Almost every building in the world is heated by a fire in the basement. And whether you're burning natural gas or you're burning propane or you're burning, if you can believe it or not, there's still 10 million homes in the US that burn either propane or heating oil, literally a tank of gasoline in the yard that heats the house. But whichever one you're burning, it's 80% of the emissions in buildings is heating and cooling.
Hi, everyone. Welcome to the Climate Confident Podcast. My name is Tom Raftery, and with me on the show today, I have my special guest, Dan. Dan, welcome to the podcast. Would you like to introduce yourself?
Yeah, great to be here. I'm Dan Yates. I'm the CEO of Dandelion Energy.
Okay, Dan, and what is Dandelion Energy?
Yeah, so we are the leading US geothermal heating and cooling company. We focus on residential through mid-size multifamily buildings, and we help large-scale production builders to put geothermal systems into their new homes.
Okay, and why? As in, what made you wake up one morning and say to yourself, I know, I'll set up a geothermal company?
Yeah, so we're all really aware of the transition of vehicles going from fossil fuel burning engine powered conventional cars to electric cars.
Yep.
And we're aware of how there's huge companies now that have been founded on the basis of that. And there's been maybe a lull recently in the uptake of EVs in the US. Globally, there's been no lull. And it's obvious that our grandkids, if they're driving a car at all, because it may be driven by a robot, they'll be driving an electric car. The same thing is afoot with heat. It's just not getting the same amount of attention. Almost every building in the world is heated by a fire in the basement. And whether you're burning natural gas or you're burning propane or you're burning, if you can believe it or not, there's still 10 million homes in the US that burn either propane or heating oil, literally a tank of gasoline in the yard that heats the house. But whichever one you're burning, it's 80% of the emissions in buildings is heating and cooling. And it's dirty. It leads to carbon monoxide poisoning. And it's an inefficient, and it's not where things are headed. What is happening and has been happening now over the last decade is an increasing regulatory and government push to electrify buildings and a consumer interest in having all electric homes. Geothermal is by far the best way to heat and cool a home with electricity. I can tell you more about how that works.
Let's dive into that a little bit, because I've talked a bit on the podcast before about the likes of heat pumps for heating and cooling of homes, but those are mostly air sourced. And what you're talking about is, if I'm understanding correctly, it's a ground sourced heat pump, essentially. Is that it?
So, to build off exactly what you're saying, Tom, the most common way to heat a home with electricity is an air source heat pump, which is basically an air conditioner running in reverse. The way an air conditioner works is it's got a part of the system in the house and a part of the system out of the house, and it's running refrigerant between those two parts. Outside of the house, the refrigerant gets compressed and is super hot, and you blow air over the refrigerant to cool it off. And that's the part of the system that's essentially pushing heat out of the house. Inside the house, the refrigerant is expanded and is super cool, and you're blowing air over the refrigerant to cool the air to cool the house. And that cycle continues. So, from a layman's perspective, the air conditioner is making cold air, but there isn't actually, cold isn't a thing. Cold is just an absence of heat. From the physicist perspective, what the air conditioner is doing is it's collecting heat in the house and pushing it outside, and it's shunting, it's moving heat out of the house. So that's how an air conditioner works. The way a conventional air source heat pump works is it does that in the summer, and then it literally just flips a couple switches inside, and it does the opposite in the winter. So instead of pushing heat out of the house, it's pulling heat from the outside into the house. The problem with an air source solution is that the world is working against the heat pump all year long. On the hottest day of the year, that's the day you're trying to push heat out of the house. And the air that you're blowing over the refrigerant to cool it off is super hot because it's a hot day. On the coldest day of the year, that's the day that you're trying to pull the most heat into the house, but there's no heat in the air on that day to pull enough heat in to heat the house. So what happens is on the hot days, the systems they work, but they just work less efficiently. On the cold days, that delta in temperature is so great that they actually just don't really work. So what they do is they flip over to what's called a resistance coil, which is essentially it's effectively 10 hair dryers sitting in the inside part of the system that you blow air over and it heats it up the same way that a hair dryer blow dries your hair. So that's very energy inefficient. It leads to very high bills. And so folks living in colder areas, and cold isn't just Maine and Winnipeg, cold is like North Carolina, Washington, D.C., Denver, even Houston on a cold snap. Folks living in those areas will see very high bills during those cold periods because they're running their system in that blow dryer mode. That's sort of the dirty secret, unfortunately, of air source heat pumps. And for an individual home buyer, they might be able to weather those bills. But for the grid, it's becoming a big issue. And in fact, a lot of the utilities in states that have been pushing air source heat pumps are now on track to having their peak demand be winter peak because of these mass blow dryer moments through the winter season. And that's going to lead to billions of dollars of distribution and transmission line investment just to cover these peaks. So enter geothermal. So what does geothermal do that's different? Well, instead of trying to exchange heat with the air, which is even on a good day, a pretty rotten medium for heat exchange because it's obviously not very dense and consequently it doesn't hold a bunch of heat, we exchange heat with the earth. And the earth is a phenomenal medium for heat exchange for a couple reasons. First of all, it's essentially a thermal battery that stores the sun's heat year round. So we drill down as deep as 500 feet below the surface of the house and install what's called a ground loop, which is essentially two pipes that have been connected at the bottom with a U-shaped connector. We fill them with water and antifreeze, and we can pump water down one of them and it comes out the other. So we can circulate this water through the loop in the ground. And the whole point of it is just to expose that water to the Earth's temperature. And in the top, let's say the top 500 feet, the primary source of heat in the Earth is not actually the mantle and the core. It's just the absorbed heat from the sun year round. And so you get, I jokingly call it lukewarm geothermal because the ground temperature is like between 50 and 60 degrees Fahrenheit, which is not 300 degrees like people think about with the other kind of geothermal where you're powering a power plant. But it's plenty warm in the winter and it's plenty cool in the summer. And importantly, it stays the same temperature even on the hottest and coldest days. So what we do is we circulate water through this pipe that's been buried in the ground. It absorbs the heat from the earth. We bring that into the house and we connect it up to our heat pump, which looks just like the inside part of a conventional air source heat pump. And then instead of exchanging heat with the outside air, we run that water through our system and we suck heat out of it in the wintertime and we use it to heat the house. And we pump heat into it in the summertime and we use it to cool the house. The magic of a refrigerant loop is such that we can concentrate heat. People often ask, well, if the ground's only 60 degrees, are you going to be able to get the house to the temperature I want? Yes, absolutely, because we take the heat out of the ground and then we concentrate it, and the air that pumps through the house is actually well over 100 degrees. And then, you use that to bring the home to 75, 70, whatever comfort level people want. That's all very fancy technology explanation. So why? The upshot is, on an ongoing basis, the energy consumption is half that of a conventional air source heat pump. And on a peak day, it's a quarter of what you would get from an air source heat pump. So we completely remove the peak and we significantly reduce people's bills year round. I draw an analogy to induction stoves. So why do I draw this analogy? 15 years ago, when you said, I'm going to move, this house is not going to be running on natural gas, it's going to be running on electricity. What people would picture is a crummy, old electric resistance range. And they say, oh, that's such a bummer because I love my gas stove. An electric resistance range is not as good as a gas stove. An air source heat pump is kind of like an electric resistance range. It's just not as good as a gas heater from the consumer's perspective. The only thing it does better, if you're running on a clean grid, is it allows you to eventually transition to an electric stove that's powered by renewable energy, which, by the way, in the US, we're not there yet. So even on that front, it's not beating gas today. But from a consumer function perspective, on every other front, it's just worse. You can't tune it as quickly. It takes a long time to heat up and cool down. The resistance ranges are not as good as gas ranges. Air source heat pumps are not as good as gas furnaces. They cost a lot more to operate, and they don't work as well on the coldest days of the year. Your gas furnace always works great. Geothermal is like an induction stove. So an induction stove is actually just on all accounts better than a gas range. It's easier to clean. It has even higher performance in terms of dialing it in perfectly. The range doesn't get hot because you're cooking with magnets. I mean, it's a spectacular, mind-boggling technology, right? It's just actually better than gas. And the prices are coming down now that mere mortals are starting to put them in. Geothermal is the same kind of thing. Geothermal is on every front better than gas. You'll have the lowest bills you've ever had. It's clean. It's super reliable. The heat pumps actually last 25 to 30 years, and the ground loop lasts over 100 years. It's like basically lasts the lifetime of the building. So it's as reliable or more reliable than a gas furnace. And then you have all the other benefits of being electric. You don't have to put carbon monoxide sensors in your house anymore because there is no risk of a gas leak. You have all the environmental benefits. So that's the stuff that is pushing this forward and making it what we see as an inevitable component of this electric transition.
A couple of things come out of that, I guess. The first is if you are drilling 500 feet under the house, does that mean it has a significantly higher capex than an air source heat pump, for example? And secondly, if you are significantly reducing the energy requirements of the house and reducing, therefore, the peak, is that something that local utilities should be interested in because you are reducing the peak for them?
Yes, I love, and thank you so much for pairing those questions together because in a way, one answers the other. So on the first question of, CapEx, or in layman's terms, upfront cost, yes, this has been the sole and very significant weak spot of geothermal historically, has been that it's just been preposterously expensive to put in. And that is the mission of Dandelion, is to get the cost down into mainstream geothermal. And we have been making great progress on that mission. And that's what's leading to our rapid growth. It's 10 years ago, there was, first of all, almost nobody doing geothermal in new homes. One choice would be to look at getting it retrofitted into your house. And there is a large and established but cottage industry of local installers across the country that do geothermal systems. And your typical quote will be $60,000 to $150,000, depending on the size of your house. And so 1% of US homes have geothermal. There are a million geothermal installations in the US, and there's tens of thousands, bordering on hundreds of thousands going in every year. So it's like, it is alive and cooking. The systems are just rock solid. All the technology is proven. It's not a risky new thing. But at that price point, obviously, it's very similar to solar in like the 1980s, where you had two categories. You had like the zealots who are like, I'll do it at any cost. And then you have rich people who are like, this is an interesting, and sort of technology technophiles who are like, this is an interesting thing I want to invest in, and I'm planning to own my home for 25 years and it'll pay back. And so I can justify it. So what we've worked on is getting that cost down. And we've done a number of things to bring it down to where our pricing now is in the sort of $20,000 to $30,000 range for a new home, all in, compared against what a conventional system will be in a new home, which would probably be, call it $5,000. So we have radically collapsed the upfront cost, and we're continuing to innovate and drive that cost even further down. And we have a number of, it comes in our design of the systems, in our engineering, and actually in our heat pump capabilities through our existing partners. And then the second piece of it, though, is the second part of your question, which is wouldn't a utility be interested in this? And yes, it wouldn't a state government or a regional operator who is in charge of managing capacity, are they interested in this? And the answer is yes. And so what has happened in the last 10 years, and it's continuing to happen, there's a steady drumbeat of progress to our benefit here, is states have been rolling, and the federal government have been rolling out incentives to offset the upfront cost. One of the few beneficiaries of the One Big Beautiful Bill Act on the environmental front last summer, because it was, let's be clear, not an environmentally friendly bill, was
nor was it beautiful.
yes. Yeah, but there's more to be said on that on another podcast. But we were actually one of the beneficiaries because it was clarified that geothermal systems can be leased, and that has allowed us, and the commercial tax credit was preserved. And so we are now in a place, we've launched a leasing offering in conjunction with one partner, and we're soon going to have another partner on our platform where there's a 40% tax credit that comes right off the top for the install of these systems. So we get 40% from the federal government when we do a lease system. And then at a state level, there are a number of different incentive structures. In some states like Colorado, there are large rebates directly from the utility that are in the tens of thousands of dollars. And in a number of states now on the eastern seaboard, there's a program called GRECs, which are geothermal renewable energy credits, that can also total tens of thousands of dollars worth of value in terms of incentives. And so if you take the math that I just gave you, and the caveman math is essentially, I've got about $10,000 to $20,000 that I've got to reconcile to bridge this gap in a new home. What we're seeing is that in a lot of these states, the incentives actually pay for, even in many cases, more than pay for that difference. And so it becomes a cost savings for these builders to put in the systems.
Okay, and is it exclusively new homes, or could people retrofit it to their existing homes?
It's both. What we've chosen to do as a company, and we made this decision almost 3 years ago now, is that we've evolved towards primarily focusing on new homes because we see it as the tip of the spear for driving costs down and scaling our business quickly. But everything that I described is available also for retrofits.
And does leasing fundamentally change adoption curves, are you finding?
So we just got started with it, and where we've launched it and put the most focus initially is in Maryland. And our pipeline now is almost 100% lease jobs in Maryland. It's a slam dunk there. It's very exciting, and it is driving adoption meaningfully. The other thing I'd add that has been really exciting news for us in the last just quarter is we have a very large project in Colorado with Lennar. 1,500 homes. We're in almost half of their communities across the Front Range, and they started completing homes in Q4 and selling them over the last 3 to 4 months. And the energy and enthusiasm in their sales organization for selling Geo is just off the charts and is so exciting for us because we knew geothermal was a great product. We believed that it would make a difference, but they're selling a home, and the home has a lot of capabilities and characteristics. And people want to talk about the layout of the bedrooms and how many cars can fit in the garage and the siding, the knobs on the stove. There's 1,000 things, right?
Mm-hmm.
Would Geo make a difference? And we're seeing that it is. Lennar actually just shared with us, and I can't share the numbers, but they have statistical data now that shows that their conversion rate on Geo homes is higher than on non-Geo homes. And anecdotally, their salespeople are raving about it. And my favorite part is that most of the sales reps are starting their tours in the basement because they want to show the customer the geothermal system. And the quotes I'm getting are things like, "We never used to talk about the HVAC, like zero. And now it's a selling point in every meeting with the customer." The idea that for builders, the incentive landscape is such that they sometimes get paid to switch, and it's a real differentiator, especially in this market where production home building has had to contract recently and there's like a lot of excess inventory. It's a big deal for them.
And I saw that a DOE analysis, the Department of Energy analysis, suggests that widespread geothermal could avoid 24,500 miles of new transmission. So, with that in mind, is geothermal actually a grid infrastructure strategy disguised as HVAC?
I think that's how I like to think about it. Yeah, that's exactly right. It's essentially a form of distributed infrastructure. So the utilities and the regulators have a choice. They're either going to invest in these tens of thousands of miles of line, or they can just incentivize geothermal, and each one of these wells effectively acts as a replacement for additional transmission and distribution infrastructure. And they last 100 years, and there's no imminent domain problems. There's no easements that you need to get. It's a lower maintenance and lower complexity solution to this problem.
And if the incentives change or ITCs shrink, do the economics still hold?
That's the path that we're on. I would analogize to solar or to electric vehicles. In the first 10, 15 years of their rapid mainstreaming, they needed these incentives. And now you're seeing on both EVs, which are a tremendously complicated technology, and solar, which is frankly less complicated, that the costs have come down so far that they can stand on their own without incentives. And we're ambitiously charting that same path. That said, for the reasons we just discussed, which is that geothermal is explicitly serves as a form of grid infrastructure, our thesis is that the steady state will not be no incentives, but there will be a continued level of incentivizing of this system on an ongoing basis because it serves this broader purpose.
And if they are leased devices, does that mean they are connected devices, that there's a cloud-based app somewhere that the owner can use to control from their phone, and that Dandelion, the company, has access to the data as well?
Yeah, that's a great question. And it's a wise connection you made. So all of our systems come with the option to have monitoring and cloud-based connectivity. As a general matter, because it costs around $500, our builders often don't include it in their base package. A homeowner can always choose to add it. And then, but then you're right, on our lease systems, we include that by default.
Okay. And so in that scenario, if you have access to 100, 1,000, a million geothermal homes, you become a virtual power plant for a utility company potentially.
Yeah, there's a possibility there. I would say the biggest benefit that geothermal brings does not require dispatching, because the benefit is by design, the system doesn't ever trigger this aux or auxiliary heat system.
Right.
And that happens automatically. So there is a secondary dispatchable load dimension to this, but we've already cut the peak 75% out the gate. We're not as focused on the virtual power plant strategy for that reason. It's like we're base load, in a sense, peak reduction that's coming automatically.
And have you spotted any surprises in the data you're getting from the geothermal homes?
It's worth putting in context. Dandelion's been around for almost 10 years. We've installed nearly 5,000 heat pumps, and we've been monitoring many of them for many years. So we actually have quite a robust set of data. And initially, the business started selling direct to consumer. So we would offer monitoring to those customers, and many of them took us up on it. So we have interesting longitudinal data across many homes in many years. I'd say the most interesting and useful thing from us looking at the data is really mostly corroborating our designs and our methodologies. What we have uniquely, I think, is we have really clear visibility into the dispersion of results. You design a system, and then it's a construction project. There's always details that go a little bit left or right. So what you end up with at the end, and then that dispersion of results allow us to tighten our error bars and have allowed us to trim fat out of the system. Conventionally designed systems have layer upon layer of buffer. I can make this very concrete. When you put in a geothermal system, you want to drill as little as you can because drilling costs a lot of money. And the simple test of did I not put in enough loop is in the middle of the winter during a cold snap. If you don't have enough ground loop in, you're going to suck all the heat out of the earth. The water coming back into the heat pump is going to be too cold. And the threshold for these systems is the water needs to stay above 30 degrees. Can you start to fall below that, you're going to have a degradation in performance. You won't be able to heat the house. You won't hit your capacity. What I'm saying is close enough to be accurate. So if you have a system that is finely designed, on the coldest days, it should get close to 30 degrees. I have put a system in my house with the conventional non-Dandelion approach because I live in DC and Dandelion isn't doing retrofits in DC. And on the coldest day of the year this year, and DC had the coldest, longest cold snap in 150 years this year. So this is not just your average cold snap. My system was still operating at 43 degrees Fahrenheit, which is indicative that I have probably double the ground loop that I need. And I had to pay for it. And I paid out the nose because it's not a tuned system. And that's just business as usual in the geothermal industry. So that's a huge part of what Dandelion has done with this. Critically, we've done it safely because we have this closed loop of data coming back that tells us that our system designs are working.
And if we fast forward 10 years, what percentage of new homes at that point will be geothermal, do you think?
We have two goals in mind. For Dandelion, we always talk about, and you'll see this in our announcements, the day we get to 10,000 homes is day one for us. It's like, okay, now we actually matter. We're in a real business at a scale that is worth talking about. And we're on a fast path to that. And we think we're going to be there pretty soon. That's still only 1% of US homes, US new homes a year. Where we think we ought to be is we think the geothermal system should be easily 30% of US new home construction. And there's no real reason why it isn't. Essentially anywhere where you have a meaningful heating and cooling bill, geothermal is the better answer.
How replicable is this model outside of the US?
Well, actually, the place that has the most concentration of geothermal in the world is not the US, it's Scandinavia. So very replicable there. They're the leader. It's expanding into Germany and Poland and all through Northern Europe. It's getting increasingly popular in the UK. And then I don't know, I know there's some geothermal going on in Korea, but I'm not as familiar with what's happening in Asia.
Okay. Quick lightning round of questions. Are you up for that?
Yeah.
Oh, great. Super. Couple of quick questions and one sentence answers. So, if you were building a new home today in a cold climate, air source, heat pump, or geothermal?
100% geothermal.
That was an easy one. Okay. For decarbonizing heating at scale, speed of deployment, or grid resilience first?
I think they're actually both the same thing because what we're running into is the grid is becoming the limiting factor on speed of deployment.
Okay, cool. If policymakers have 10 billion to spend, should they build new transmission lines or reduce peak demand in homes?
Definitely the latter, reducing peak demand.
And electrify everything as fast as possible or electrify in ways that minimize peak load?
I think, again, it's actually the same thing. The thing that's going to hold back electrifying is going to be peak load.
Upfront subsidies for homeowners or long-term grid investment?
I think the right calculus here is what is the cost per kilowatt and kilowatt hour of the investment and how much friction is there in achieving that investment. And what we see is the cost per kilowatt and kilowatt hour of incentivizing geothermal is very low, and all of the broader political issues around larger scale investment like eminent domain and easements all evaporate when you do geothermal. Sorry, that was two
And
sentences.
never mind, we let you off. A left field question for you. If you could have any person or character, alive or dead, real or fictional, as a champion for geothermal home heating, who would it be and why?
That's a funny one. I don't have any idea. Who'd I want to be the flag bearer of geothermal? To me, the ideal flag bearer is an everyman. That's the point here, is that geothermal is being mainstreamed and it doesn't require Tony Stark and it doesn't require the pocketbook of Jeff Bezos or Bill Gates. It's Homer Simpson. It's your everyman who just wants to have a lower bill and a more reliable system and have a home with better resale value.
Fantastic. Fantastic, Dan. We're coming towards the end of the podcast now. Is there any question that I didn't ask that you wish I did, or any aspect of this we haven't touched on that you think it's important for people to think about?
I think we've hit a lot of the key points. We're growing like crazy and we're hiring. And I'd love to point any one of your listeners who are interested in joining the cause here to check us out at dandelionenergy.com. And obviously, if any home builders who are interested in bringing geothermal into one of their communities, we are now doing geothermal nationwide. We're especially focused in the Mountain West, the Mid-Atlantic, and the Northeast, but we're doing projects all over the country and are always eager to meet new builders who are interested in learning about geothermal.
Okay, Dan, that's been really interesting. If people would like to know more about yourself or any of the things we discussed on the podcast today, where would you have me direct them?
Yeah, please also visit us at dandelionenergy.com and you can learn all about what we're up to, how we do it. And, you can always reach out directly to us through the contact form and the emails.
Great. Dan, that's been fascinating. Thanks a million for coming on the podcast today.
Thank you so much for having me.